Nazani. I am an assistant professor of civil environmental engineering at Lehigh University. I serve as the chair of this task committee, the Water Energy Cooperation Water Energy Task Committee, which is under ASCE EWRI. Thank you so much for joining us. I understand that for some of you this is too early, for some of you this is too late. So either way, I truly appreciate your presence. I will give a little bit of background about the task committee, and then we will go ahead and start the webinar. We started this task committee a little bit before last year's EWRI Congress around June. And then officially we were approved in August 2024 as one of the standing task committees of EWRI. Lina Sella, who is an associate professor of UT Austin in UT Texas in Austin, she serves as the co-chair of the committee, and my PhD student Saskia Putri at Civil Environmental Engineering at Lehigh, she serves as the secretary of this task committee. This is the first webinar of the first series of webinars that we have planned for this task committee. So in the first series, the focus is going to be training the non-electrical engineers, specifically water researchers, about the fundamentals of power system, microgrid, and how we can simulate and model them. And then the next series is going to be focused on specifically different aspects of water energy interdependencies. Today's webinar will be focused on the fundamentals of the power system, and then the second webinar, which will be in December 3rd, will focus on the modeling of microgrid. And the third one, which will be announced hopefully soon, will focus on different simulation platforms for the power systems. To introduce our speakers who very graciously accepted our invitation to present for this webinar are Dr. Demetrios Eliades and Dr. Mathaios Panteli. Dr. Demetrios Eliades has been a research assistant professor at the KIOS Research and Innovation Center of Excellence at the University of Cyprus since 2019. He received a diploma in electrical and computer engineering from Aristotle University of Thessaloniki in Greece in 2004, a master's degree in artificial intelligence from the University of Edinburgh in 2005, and a PhD in electrical engineering from the University of Cyprus in 2011. Dr. Eliades' research expertise centers on smart water network, where he focuses on the modeling, monitoring, risk assessment, and cyber-physical security of these systems to reduce water loss, ensure water quality, and enhance responses to contamination threats. His work covers computational intelligence applied in early warning systems and digital twins for real-time state estimation, sensor placement, real-time event diagnosis, and active detection methods. He has led and coordinated numerous national and European projects, including the EU-Korean H2020 Pathogen Contamination Emergency Response Technologies project. He's also involved in several industrial projects and supports various governmental units in transitioning to smart water systems. And additionally, he's actively involved in fundamental research projects aimed at designing the next generation of smart water systems. Dr. Panteli holds an assistant professor position within the Department of Electrical and Computer Engineering and KIOS Center of Excellence at University of Cyprus. He also holds an honorary lecturer position in Department of Electrical and Electronic Engineering in Imperial College London, and he's currently an Andre Jamot chair professor in University Libre de Bruxelles, which is the Royal Academy of Belgium. Prior to joining UCY, he was a lecturer at the Power and Energy Division of the University of Manchester, serving as the deputy lead of the Sustainable Energy Systems Research Cluster. Through his academic career, Dr. Panteli has successfully developed a multi-million research portfolio, attracting funding from research councils, industry, and European commissions. He has published over 100 research articles in high-impact peer-reviewed journals and conferences. And Dr. Panteli is an IEEE senior member and IET chartered engineer, and the chair of the CIGRE Working Group C4.47 Power System Resilience and the CIGRE Cyprus National Committee, an invited member of multiple IEEE, CIGRE, and CI-RED working groups, and a fellow of the Higher Education Academy in UK. He serves as an associate professor, associate editor in IEEE Transactions on Sustainable Energy, IEEE Journal of Modern Power Systems and Clean Energy, and IET Renewable Power Generation. He is the recipient of the prestigious 2018 Newton Prize, and he has led the team receiving the 2022 Innovation Radar Prize by the European Commission. With that, I will ask Saskia to just go over quickly some logistics about the webinar. And if you have any suggestions for the future webinars that you would like to hear, or you would like to for us to plan that, please feel free to reach out to any of us. You can reach out to me or Lina or Saskia, and we will be very happy to consider different aspects of water energy systems. Saskia?
Thank you, Dr. Mozeni, for the introductions and the introductions to the speakers. So for today's webinar, we will dive into the introductions to power systems by Dr. Eliades and Dr. Panteli, and after the presentations, we will have a Q&A session. So for participants that have attended this webinar, please feel free to submit the questions through Zoom chat, and then we will discuss it after the presentation. And these are the QR code for the slides, the green one. And then if you are interested in the ECO-WES task committee, please feel free to also scan the QR code for the registration. We are excited to welcome you and join us into this task committee, and to get to know more about what happens in water energy systems development. You can also join us through LinkedIn using this QR code. Without further ado, please, Dr. Eliades and Dr. Panteli, to start your presentation. Thank you.
Great, thank you. Let me just share my screen. I think this is the right one. Maybe share with sound. Okay, let me know if everything is okay.
It's in the presenter mode, Demetrios.
Yeah, I will just go to presenter mode. Just give me a moment. Now, is this okay?
Yes.
Okay, hide floating meeting controls. Perfect. So, hi everybody. Good morning and good afternoon. It's really a great opportunity for us to present the topic that we really are, really passionate about. So let's dive in. Just a moment. So, what are the learning objectives for this lecture today? Is to understand the fundamental components and functions of power systems, to identify the interdependencies between water utilities and power systems, to learn about the role of renewables and smart grid, and also to understand the key research challenges that power systems are facing, that we need to address, to discuss practical case studies, highlighting the water energy nexus, and also, in the end, of course, our vision is to foster a collaboration between water engineers and power engineers. So water and power are connected. For instance, when there is, of course, a problem in power systems, like a disruption, a blackout, or a power outage, this will definitely affect the water supply as well as the water production. On the other hand, the lack of water can actually cause blackouts, for instance, if the hydroelectric power plants are not able to operate. So there are a lot of leakages, and of course, we already know that. So let's dive into why, what power systems are at a very high level. And I think that, yes, okay. So traditional power systems consist of four main stages. The first is a generation part, which is typically happening at the power plant. Then is the transmission stage, then distribution phase, and then the consumers. We will go into the details of this step by step. So let's dive into this. The first part is, of course, the generation. And here is where electricity is produced. So we have the conventional power plants, but also nowadays we have wind renewable and also photovoltaic renewable. So the electricity produced here is transmitted in a high voltage over long distances using high voltage lines. Usually these are greater than 35 kilovolts to reduce losses. And this part is usually operated by a transmission service operator or a TSO. Next, so essentially this moves electricity towards the cities. So close to the cities, this is transformed into a medium voltage. And this is essentially is to move around the electricity around the city, let's say, for example, through a ring network. And this is operated usually by a distribution service operator. Now, the electricity that reaches our home, of course, is not in this stage because here is between 35 kilovolt and 1 kilovolt. So this should be reversed. So the electricity reaching your home should be less than 1000 volt. So this is a low voltage. So we step down voltage to low voltage for consumer use and of course for businesses. So in a nutshell, this is how the system works. So there are some similarities with water systems in the sense that water is produced somewhere, is transported using some big pipes over high pressure to different cities, and there usually water goes to a tank and then is distributed through a large pipe network and then through a smaller network of pipes down to the consumer. So topologically speaking, there are a lot of similarities with water systems in this sense. Now, it's useful to know how electricity is generated, and this is based on a very fundamental principle discovered by Faraday, who found that when moving a magnet inside a coil of wire, this induces an electric current through the wire. And you can see in the animation over here that actually the current is not static, but actually it fluctuates. And this is actually what causes this alternating current. So motor generators actually rely on this principle. So what happens is that steam makes magnets to move within a cage of coils to generate these alternating currents. This is what a traditional generation plant looks like. So of course we don't really like the use of coal, but this is essentially the fuel that is used to boil water in this case, creating high temperature steam. This steam goes to this turbine, which turns, creates an angular motion, and this angular motion moves the magnets inside the generator. So this is what it looks like. And I have here a nice animation of how this looks like. So you can see the steam. This is the high pressure sensor, the low pressure sensor. So essentially there are blades here. So it's like a fan, and this causes this constant turn. So in a nutshell, this is what's happening, and it causes this angular motion. So the next part, this enters into this generator, and essentially this is what it looks like. So you see you have the rotor that spins the magnets over here, and you have the stator, which is essentially where the current is generated through this physical phenomenon. So just a moment. And this is what it looks like in practice. So this is an example. Now, it's another important concept that you need to be aware is that these generators, they operate, we call them synchronous generators in the sense that they try, the goal is to have, let's say, 3,000 rounds per minute. So this angular velocity should be around 3,000 or 360 rounds per minute, which corresponds to 50 or 60 hertz, 50 in Europe, 60 in US, etc. And essentially this is regulated And this is what causes frequency in the network. So essentially, so essentially this thing that spins all the time, it's applied, it's an electromagnet powered by a DC supply. And the stator we already mentioned is the wires essentially that create this electric field and this current, that receive the electric field and generate the current. And also another interesting thing is that the three phases that you may be aware, essentially they have this difference of 120 degrees phase shift, essentially because these coils have this shift of 120. So this is how they're kind of wired in the system, in the stator. So this is very important because this when there is a problem, this could change. And our systems that operate the machines are actually the equipment that we have in our house or in our industry. It's designed to operate at 50 or 60 hertz. Now we mentioned about the steam generators. We also have some other type of power systems like the hydropower. This is dispatchable. It means that we can decide when and how to use it. And essentially, this is for dams. In dams, we essentially release water through a gate. It goes through a turbine here, and this produces electricity. And we can use this also for pump storage, which is essentially when we have excess wind or solar energy, we can pump water from one reservoir to another reservoir at a higher elevation. And it's interesting to know that 8 out of the 10 largest power stations in the world are actually hydroelectric. Now, another type of generator that you are familiar with is, of course, wind turbines. Now, if you've seen a wind turbine moving, the blades are not really moving that fast, right? So essentially, there's a gearbox that increases rotational speed to 1,200 to 800 rounds per minute. And of course, it's not close to the 3,000 that we mentioned before. So here, what they are doing is that you can convert this alternating current to a DC, and then with a rectifier, and then back to AC with an inverter. So the goal is to keep the frequency and phase aligned with the grid. Now, what happens when there is a change, when there is a problem, and when there is, let's say, an increase in load? What happens to these power systems? Let's focus now on the steam generator. So you saw that the steam generator is turning, producing electricity. Let's say that we have a sudden increase of inductive loads. That is, let's say we start a large water pump. So more current is needed, and this increases the electrical resistance. As a result, this slows down the rotating speed and this, of course, when you reduce the rotating speed, and by extent, the frequency starts to drop. There are some local controllers there. So there is a governor. This is a local controller system, which increases the steam flow with the aim to stabilize frequency. And so you see there are some different efforts that the system tries to stabilize, but this was actually a case where this was an event that was noteworthy. Let's say that it had this drop in frequency. So even though, because the systems are working in a very tight range, these 50 hertz, this can destabilize, big changes can destabilize the grid and affect the connected equipment. Now, also for reference, I gave you this is a picture of the high voltage grid in the US. So high voltage, this is greater than 132 kilovolts. This is more or less what it looks like, and most of the things here are interconnected. So in contrast to water systems, the power system is actually interconnected, whereas in water systems, they are more decentralized, so to speak. We don't really have, it's not easy, you don't have water pipes connecting one side to the other. And this is also similar in Europe. You see in Iceland a nice circular grid. In Cyprus, it's a combination. It has some circles here, some loops here and there, but also some more radial type of network. But I just wanted to mention, so this is a high voltage network. And so this is the AC with magenta, this color over here, this indicates some high voltage DC connection. So in some cases, you are able to connect not only with AC, but with high voltage and DC electricity, especially for islands. This is very useful. Now, let's start talking about the key elements of power systems. So we have the transmission substations, and these are the main elements of these power stations are the power transformers, the bus bars. We also have circuit breakers for security and some capacitor banks. The whole idea of these transmission substations, and you may have seen them as you're driving, essentially is to increase voltage for transmission or to decrease voltage for distribution. So a key element in these are, of course, the power transformers. So the problem is that we need to transmit the energy in long distances. And unfortunately, we have large energy losses in the transmission lines. With this equation over here, this is current, this is resistance. So the way to handle this is that you need to reduce the losses, is you have to reduce the resistance, and this costs a lot because it's an infrastructure issue, or you can reduce the current, and you can do that by using transformers. So these step-up transformers essentially reduce the current for the same amount of power. This is in principle, let's say at a high level analogy, but not an accurate analogy. This is like when we're using a pump in water systems to increase the head, but it's not the same because we actually use energy. We use extra electricity to generate, to increase the head, and also when you are reducing the head using the PRVs, of course, we are consuming energy. So it's not exactly the same. But in principle, more or less, it has some analogies. The buses are so if you are working with models, you see the word bus everywhere. So, but what is a bus? I mean, I had this question when I was studying, when I was a student. It's just a piece of metal that conducts electricity across the span. So these pipes over here are the buses, and the equipment in substations is usually clamped directly to these bus bars. They connect power sources, loads, generators, transformers, and essentially they are the equivalent of a junction. They are an electrical junction where incoming and outgoing currents meet. Yeah. So next, when we leave these substations, we go to transmission lines. These overhead transmission lines, essentially, they move electricity, and of course, we call it impedance. Essentially, is the friction due to the resistance and reactance, but it's the equivalent of pipes, let's say. Now, how do we model this transmission part? So we have the bus bars, and these are these thick black lines over here, and these are junction points for the power flow. And usually we call the PV bus if it has a generator, or PQ if it has a load. So this with the arrows has a load. This with the generators have generator. C here is a condenser or a synchronous capacitor. Is essentially, it's like a motor that runs on flywheel. Let's say it's essentially without any. It's not generating electricity. It's actually it's doing, let's say, the inverse. So we have the loads and we have the transformers, and this is a very basic, one of the most well-known benchmarks is a 14 bus system, and you may have seen in some papers. But keep in mind that what we see here is actually a national scale network. So it's not a city, an urban network. We're talking about here. These are very high voltages. So 220 kilovolt and 132 kilovolt. These are the transformers. Essentially, these are high voltage. This is a high voltage transmission grid. So we are talking about this system over here. And just to understand the scale, so we have the extra high voltage, which is this 220 kilovolt. We have the high voltage, and also if you go to medium voltage, this is within the city. And if you go to a neighborhood, you can zoom in, and this is the medium and low voltage. So this is actually a nice paper from. It's a nice paper where actually you can generate automated in an automated way this type of networks. Now, what's happening here? We have the distribution network. From the distribution substation. Sorry, you may have seen these power lines poles with 3 lines, essentially this is a medium voltage. So whenever you see these 3 lines, this is medium voltage. And it goes, and it ends somewhere like this. It ends somewhere in a pole like this. And these 3 lines, these 3 phases, they go to a transformer, and this transforms the medium voltage to low voltage. So here in this case, let's say from 11,000 volts to 400 volts. And essentially now you see the more traditional, it's typical to have these 3 lines, the 3 phases, plus a neutral, plus maybe another one for street lights, etc. Depending on the country, there are different specifications, but more or less, in a point, there is always a transformer, and there is this low voltage network. So again, this is more or less how this medium to low voltage looks like. Again, I'm giving some reference that you can use, like this one, which it's within the city, and also this one. So here, each node is essentially a house. So people working with water systems, especially with EPNet, these nodes are the consumer nodes, and this looks more like a tree type of water distribution network, the equivalent. So you see here, you have the medium voltage grid, right? And you have the transformer here. Essentially, everything below the transformer is a low voltage grid. Now, the majority of loads here are, of course, single phase. You know that whenever you plug in your television, there are 2 phases. And maybe we have some devices that require 3 phase, like heat pumps, air conditioners, and usually industrial equipment has 3 phases. So like water pumps may have 3 phases, etc. Now, it's very important to say a word about reactive power. So voltage and current. So voltage and current phase, like should be aligned. The sinusoidal signal should be aligned. Like should have the same, let's say, the same start and end during that period. However, when we have different type of loads, like inductive loads, and in the case of motors, these are inductive modes. This shift the phase. Essentially, the signal shifts. The one lag. So in this case, the current lags the voltage, as we say. So the one is behind the other. So what this means? This means that it's something that we need to pay attention, because this creates some additional reactive power. And essentially, reactive power is like, there is this analogy of a beer. So the real power is what is a kilowatt. It's what is a kilowatt is the real power, is the power you actually use to make something, to do something. The reactive power is not really used for creating work. Okay, so why do we need it? First of all, it's impossible. I mean, we really need to have something. I mean, it's like the beer and the foam. You cannot really have a beer without just a little foam. And the reason is that you have different devices in your network, and some are inductive, and some are more capacitive, and the one kind of shifts from the one direction, the other to the other, and the other to the other direction. So essentially, what we have. So essentially, we pay for this. We pay for the total. We don't just pay for the real value. We pay for the whole value. So we need to have some reactive power to compensate for the different systems we have in the system, and to protect the system. What we can do sometimes is that we can use this power factor corrections. So for instance, in a big industry, if they have a lot of inductive loads, they can add some big capacitor, etc. Or you can do this at the level of the substation. So this is an important concept to realize, that it's good to have. We don't want to have a lot of reactive power. It's inevitable to have some reactive power in the system. And we pay for the whole, beer. So we really need to find this optimal home, let's say, to enjoy it. Now, As you are of course aware, power systems, fossil fuels are contributing to carbon dioxide emissions. So we need to integrate renewables, wind, solar, electric vehicles. And the problem with this is that it's highly variable. So here you see wind and photovoltaic generation in Cyprus, and there is a lot of fluctuation. Of course, sun is only available a few hours per day, and wind fluctuates a lot. So it's a matter of stability. Also, the problem is that when sometimes we have too much generation. So what you see here is called the curtailment. So it means that it's the involuntary reduction in the generator's output due to the restriction of the operator. So what this means is that in Cyprus, in summer, so we had to curtail, so we had to stop producing renewable electricity from renewables, which would have been like this, because we could not consume nor store this excess electricity. So it's a big issue, and this is actually a big problem that we need to solve, and it's a challenge that can be solved using pump storage, as I mentioned before. Now, here, also for this integration of renewables, we need some advanced technologies. So we need innovations in power electronics, and these smart devices that I'm going to mention in a while. In the end, this will allow us to go from the traditional power systems where the power flow goes from the power plant to the consumer to a more bidirectional power flow, which is, of course, more complicated to achieve. Now, we have a number of challenges. We have the increased demand. We have the electrification of the transportation sector. So we have the electric vehicles that act also as batteries. So they can take electricity, but they can return electricity back to the system. We have electrification of the thermal loads nowadays. So we have more heat pumps, more air conditions. So the power systems usually operate within their physical limits. And a challenge is also the absence of smart meters. So you know that in water systems, a similar problem because the absence of smart meters makes the systems, especially at the distribution level, unobservable. So smart metering is something that is being more and more, let's say, applied nowadays with these AMIs, advanced metering infrastructures. And of course, like the same as in water systems, it's not just for billing purposes, but we can use these meters to enhance our situational awareness of the distribution grids. So because before we didn't really have this information. So there is another aspect in sensing. There is high frequency sensing. Let's say that this is equivalent of high frequency pressure sensors in water systems. These are the facial measurement units, or PMUs, as they are called. Essentially, they are GPS synchronized, producing, let's say, 100 measurements per second. And this allows the fast and dynamic monitoring of power system operation. This is especially for the high voltage and medium voltage distribution grids. And of course, we have additional smart devices that are being integrated. Essentially, these are devices, and some are IoT enabled, that can receive coordination signals to act as flexible actuators. And I'm saying this because at some point we need to connect water systems and power systems. So some of these devices will be involved in the decision-making process and in the exchange of information. So this is more or less how this will look like. For instance, if you have a demand response system with a retail, so you have the retailer here, you have your smartphone consumer. So essentially, this is the system, the smart meter, and essentially you have here controllers, local controllers, which maybe they can control the appliances in a house, but also some large pump or valves or anything else that consumes electricity in the water domain. Of course, we cannot. The next step, of course, is to discuss the concept of microgrids and mini grids, because this is where they come in. Now that we have the ability to control, we can now operate independently, even in island mode or connected to the grid, in a better way, these communities. And so this can be small or can have different sizes, but the idea here is that they have these local renewable energy sources. We have the photovoltaics, we have batteries in homes, we may have the electric vehicles, and essentially it serves as a backup power if there is a grid outage. So this opens and it operates by itself for some time. It also, the idea or a vision would be to also support emergency situations. So in Africa, actually the UNDP actually has a big investment in mini grids in Africa, specifically for these rural communities. So this is actually a very big innovation that is happening right now. And I think there are a lot of interdependencies here with water systems. Storage, okay. I mean, just to say that storage systems are increasing more and more, and we have different types. You have your traditional batteries. You have, of course, the hydrogen pump that I mentioned before, hydrogen fuel cells, mechanical flywheels, etc. At the ICT side, the power systems are facing the same challenges as water systems. A lot of different devices, they need to communicate, and they need to interact, and you need to make some decisions at the centralized level. So more or less the same challenges with cybersecurity, cyber physical security apply to power systems as they apply in water systems. Now, summarizing this, from traditional power systems to smart grids, we need to develop new inverters, new energy storage devices, integrate advanced metering infrastructure, adopt digitalization across the whole cyber physical spectrum, as well as develop online monitoring and automated control schemes. Now, some key concepts that you should know. First is a state estimation. Essentially, this means when state estimation is mentioned in the power systems concept, it's actually similar to water systems. Essentially, using a set of sensors, and you have the model, estimate parameters which are not measured. So what are the what is the phase in this bus if I'm, and even if I don't have a sensor, or the voltage if I don't have a sensor at that bus. So estimate what I don't measure. Power flow essentially is a numerical solution of power systems, considering the active and reactive power and voltages. And here, it's very similar to the way we solve the hydraulics in water systems. So essentially solving in an iterative way a problem, a set of algebraic equations. The unit commitment problem is the optimization problem for scheduling generator operation. So which generators to operate under certain conditions. And the economic dispatch is to optimize the generator production at the lowest cost. So these are very, very crude definitions just to get an idea. And I'm pretty sure that Mathaios could say a lot more about this. But at the moment, I'm just trying to give you a high-level overview. The demand side management is also when you are trying to optimize which loads to reduce or shift to maintain stability without curtailment. And this is actually many of the work that we are doing, I think, in water and power fits in. So how do we shift loads essentially to optimize, to maintain stability? And by stability here, we mean, not have, the frequency should be as close as possible to the one designated, like 50 or 60 hertz, or that we don't have under voltage, etc. Now, we're going to present tools in a different lecture, but I just want to give you like the very quick and dirty how you do this power flow, let's say. So there are these tools like Panda Power that you can easily load this 14-bus system, run power flow analysis. So people working with EPNet Python toolkit or the EPNet MATLAB toolkit or Winter, it's something. It's the same thing, but for power systems. And essentially, it solves a Newton-Raphson method, which it solves does some matrix calculations, and in the end, it produces some results, which are just a note in power systems. These are given in per unit. This is a normalization of results with respect to a reference bus that has some reference voltage and phase. So essentially, you just multiply this with the nominal value and you get the appropriate value. But typically, the results are given in per unit. It's to assist in solving the equations. And people, because I see that a lot of people are using benchmarks, so you can actually find, let's say, official or good quality IEEE power electronics society benchmarks in this URL. You will find it in the slides, both for the power flow, also for the unit commitment problem. You can find these benchmarks. So I'm closing with this. So there are a lot of challenges. People in water and energy, and people working in water energy nexus, they are studying different challenges from a different point of view. Usually there are some similarities, but also some differences. So people in power systems, they typically solve the problem of co-optimization of power and water systems, the problem of demand response and flexibility, the integration of renewables, storage in tanks and reservoirs, and load shifting, which is kind of similar here. People in water doing more water-oriented research, they are more focused on energy efficiency through, let's say, pressure management, leakage reduction, but also in recovery from water and wastewater treatment. Also, energy recovery using pumps as turbines, pads. Also optimizing pump scheduling and studying the climate change impacts. So by saying this, this is where my presentation ends, and now I pass the floor to my colleague, Mathaios. And Matheo,
Thank you, Dimitri. Yes, I will be sharing my screen, yes. Yeah, I'm always amazed, Dimitri, how well you describe our area. Being so knowledgeable, that's great. Okay. For some reason, just give me a second. Okay. Okay, I think you can see my screen now, right?
Yes.
Okay, great. So thank you, Dimitri. I will try to keep it short, given that we have only 15 minutes to allow hopefully some time for questions. So Dimitri's mentioned also that we're moving towards a more multi-sector and multi-vector systems. So we're having the integration of different sectors, including water energy, as well as energy carriers, as we call it, where we have hydrogen, heating, and gas, and so on and so forth. So I will be focusing here on the water energy work that we did, especially within the Future Downs project that we were leading when I was still with the University of Manchester. So there's a video here, but I think you can play from the slides, so not to spend more time. So Future Dam was a cross-disciplinary project. So we're very fortunate to have water and power engineers working together for 4 years on this project. So it was at the river basin level, as we'll see later. So this actually led to very tangible, concrete and practical tools that are currently applied by the African partners, mainly in Eastern Africa, but as well as in Ghana, which will be the case that I will show later. Okay, this is the video, which we'll skip. So traditionally, Dimitri's mentioned as well that water and power engineers were working quite in silo. So you have your water system and with your reservoirs, hydropower, water demands, and so on. And we have the energy system on the other side, which we're making the assumption that we can have as much water as we want and as we need for covering basically the energy demands. But through the Future Downs project, we're starting realizing that, especially in countries where we have this kind of multi-resource river basin systems, where water can be used for reasons way beyond just electricity, for agriculture, irrigation, and so on, the problem is not that simple. So we cannot simply make the assumption that we can use as much as water as we need for hydropower. So we started with the colleagues from the water side to see how we can develop this kind of integrated spatial water energy model, as I mentioned, at the river basin level, So we used as a coupling point basically the hydropower and between the water and the energy model. And as we can see in this simple diagram here, we have the energy model and the water model, but now they are not interdependent, but they are interdependent. So this communicate through a communication engine that we developed, where they exchange some critical information in order to co-optimize the operation of the two systems. So to do that, we developed a Python open access platform for energy systems, for water systems, but also the PinSim model, which is basically the engine that brings together the water and the energy models to operate as one. So for this, we also developed some novel AI systematic criteria and design frameworks in order to assist the decision-making in the water, energy, food, environment resource systems. As I mentioned earlier, this is very important when we're talking about river basins, especially in developing countries, using integrated spatial explicit power water resource simulator. So this is very important, and because we spatially interconnected the water and the energy system, as I will show later as well in the Ghana case study and the Nile Basin case study. So what this basically is, we have the integrated river basin and power system simulator. So we have the two systems working together, exchanging information and so on, which passes basically the objectives into a multi-objective AI-based search algorithm. So the objectives can be, as I will show in a bit, these objectives span across different sectors that we have in a WEFE environment. And then this kind of optimization model, returns the decision variables and back to the simulator. And these decision variables can be to build more infrastructure, use more renewables, change the operating conditions of the hydropower, and so on. So the case study I will be using to demonstrate this is the national scale Ghana hydrothermal electricity transmission system that we used in collaboration with many Ghanaian authorities. So Ghana is basically comprised mainly by hydropower, about 50% of the generations produced by hydropower. Then we have gas and oil, and they wanted basically to encourage and to aim for large-scale development of variable renewable energy sources, mainly supported by the Akosombo Dam, which is the dam which is here in the south, is the largest generation plant installed in the country. But having here in the south created the problem how to transfer power basically from this dam to the north of the country. So what you can see here is basically the model at the national scale that we developed from Ghana, where we can see that we have wind farms, solar PV, batteries, the whole electrical substation transmission system I was explained earlier by Demetrios. But we also have irrigation infrastructure and also water. So we have everything simulated into one single platform. So we had some design challenges. We had to minimize basically the hydroecological disruption, also reduce emissions, and meet the future energy demands. So basically, you can see that the objectives and the challenges we had to deal with span across beyond just electricity. We had the limitation of non-built-in new dams, however, so we had to see how to better operate the existing ones. Then these objectives, which I will not go through, but as I said earlier, they span across many infrastructures. The decision variables we had was to build more renewables to make the system greener, basically, as Demetrios mentioned earlier, to reduce as much as possible the CO2 emissions, to expand the transmission system, and to change the reservoir operation. And we had different intervention scenarios, which basically kind of meets these three options. So we have here in this parallel plot diagram, we had on the left, we had the objectives that we had to meet, which is basically increasing the agricultural yield, reducing as much as possible the annual load curtailment, the emissions, and the hydroecological alteration. And the more we go to the top, the more preferred the option is. And on the right, we have the decision variables, which, as I mentioned, is including more renewables, expanding the grid, and including more dispatchable bioenergy generation. I'm sorry. So each of these lines that we have here reflects one investment scenario for Ghana. And you can see that each investment scenario behaves differently for each of the four metrics we have across this WEFE nexus that we used for the Ghanaian system. So instead of recommending one or two or three investment portfolios, we thought of representing these portfolios to the Ghanaian authorities And what they can do is basically they can start adding filtering to these parallel plot diagrams to filter out the scenarios, the investment scenarios that better serve their own purposes. So for example, if we're going to be putting some filtering into the transmission line expansion, let's say we don't want to expand the transmission system, then we can see that basically this operates at a base load. So we have a reduced hydrological alteration, but the renewables is not that high penetrated into the system. So we are reducing the hydro impact, but we are not optimizing the penetration of renewables. On the other hand, if we do more hydro peaking from the big hydro dams they have in Ghana, in order to follow the intermittency of renewables, we have a high impact from the hydro perspective, but we maximize the penetration of renewables, and we also kind of improve the area local attainment and the emissions because, of course, we introduce more renewables into the system. Then we can start playing by increasing the transmission system and so on to see the optimal, the more compromised option. And the final compromise solution that we came up for Ghana is basically something that we see in this diagram, which is basically updating the operating rules for the hydro to do a bit of more hydro peaking instead of using hydropower just for base generation, and basically interconnecting also the different regions in Ghana and introducing more biogas soaring generation in the northern region of the country. So this, if you like, is the compromise solution as a recommendation from the project for the future energy and climate planning of Ghana. We also had a case study on Nile Basin, which unfortunately, because of little time, we don't have time to go through into details, but this it's a very nice simulator, it's a very nice model, which basically interconnects all 13 countries of Eastern Nile, both from the energy and the water side. So this model can actually be used in very much detail for any purpose you want, either operation of planning of the integrated water energy model of the Nile Basin. We also developed other models and other tools when it comes to policy design. So we basically developed these simulation-aided models in order to support the policymakers across different sectors to sit together and make a decision basically about the best scenario to meet the sustainable development goals in multi-resource river basin systems. So we have also some relevant articles publishing high-profile papers. We have one in Nature Sustainability and one in Nature Water. I put the links here if you want to find out more information. So this was for transmission. Now we do also work for distribution, also in collaboration with the colleagues from Technical University. I saw Avi and Gal on the call as well. So the idea here is to see how can basically coordinate the two systems in order to better respond to an emergency. So how can share the resources between the two systems and the flexibility between the two systems in order to better react in an integrated way rather than in a silo way to an emergency, either from the water side or from the power side. And we develop different ways of trying to basically interconnect the two models in order to exchange resources in case of an emergency. Now, I will close with a few words on the task force that we have in IEEE, which I'm a member of water power systems. So in this task force, which we had the pleasure of hosting also Parag in Seattle, and Javad also they attended the meeting and they provided very nice insights in the discussion. So we had big 6 more generic thematic areas on planning, operations, resilience, policy and economic, hydropower, marine energy storage, as well as data requirements and analytics. So we had these thematic areas, and each of these thematic areas had one lead. I was leading the one on resilience of interconnected water power systems. And here you can see basically the chair, co-chair, and secretary of the task force. So this task force basically kind of concluded now, and we're trying to see the next steps, how to take this further. Hopefully we'll try to make this a working group. So if you are interested in joining, please let us know and we can share the details with the chair committee of the task force. We published a report, which is a quite extensive and very nice report, discussing basically the challenges and needs, the state-of-the-art tools, but also it recommends and suggests some short, medium, and long-term research and applications for each of the 6 thematic areas that I described a bit earlier. This is just an example of how a snapshot of what it's in the report. So this is just for resilience. So basically, for each of the 6 thematic areas, we try to see the impacts of power to power, power to water, and water to power, and to capture this kind of interaction between the 2 infrastructures across the 6 thematics that we have in the task force. And we know that the reports are, of course, too long to read. So we recently published also an open access paper and journal paper where we discuss this kind of global research priorities for water and power systems if you want to have a look. And as Farah mentioned, there was this committee circulated an email and that there will be a webinar on December the 10th, which is free to attend. And Farah, your own chair, is also presenting in that webinar along with some other colleagues from the task force. So if you want to register, the link is here, and we'll be happy to see you in that webinar as well. Okay, so thank you very much. I hope I didn't rush too much, given the time that we had.
Thank you, Dr. Panteli and Dr. Eliades for the presentations. It was very insightful, and I hope everyone can enjoy the presentation and learn a lot about the power systems. So we have multiple questions here from the participants. The first one is, how can we typically address the different operational time scale requirement in water and energy systems? Because it's very different. For power systems, typically we have a much faster time scale, but in water, we can use a slower time scale. So how can we address those differences?
Demetrios, do you want to go first or should I go first?
No, I think you go first because of the examples that you gave, maybe.
Yeah. So when we first started working on this, and we are assuming in power system that hydropower is immediate. So we use it basically for fast response, the hydropower. But from the water engineers, told us that that's not realistic. So in our models, in this kind of integrated model that I mentioned earlier, we're also considering the hydraulic routing of water and the constraints and the delay that is basically added into the whole integrated simulation. So we have the full water model and the full energy model integrated together. Also considering the delays that are added from the water and the energy side. I see Farah says that we don't have time, so I don't want to go into more details, but I will be happy to follow up with more details via email if that is possible.
So, Dr. Mozini, should maybe we can,
if folks can stay on for a few more minutes to answer at least the questions on the chat, that would be great. But if you can't, please feel free to leave. And then if you have any questions, feel free to reach us through email as well.
No, happy to stay for a few more minutes. It's okay with me.
Thank you so much.
So to come back to this operational time scale, if you want, on the time, that's a very important thing. And because as Saskia mentioned, electricity is transferred basically, instantaneously. And water, there's a big delay there. Not big delay, compared to electricity, there's a delay. And that is something very important. That's something that we as power system engineers were not considering to the extent that we should be considering. But that is included in our models, as I said earlier, with the hydraulic modeling. I'm not an expert in water, of course, they provide those models to us. And we plugged them into our model to introduce these delays and the time difference between the two models.
Okay. Thank you, Dr. Panteli and Dr. Eliades. Do you want to add, or we can move on to another question? So one more questions, and then we can finish the webinar. And then is there, so maybe from the presentations, we have another questions can we get a more comprehensive report or published papers related to the optimizations for the water and energy systems? Where can we find this comprehensive report as well?
I think Mathaios showed. I think Mathaios showed. I think the question was before Mathaios provided the links. So I think those are good reference points. Just to say from my side that we from being an electrical engineer, but also working with the water, like with smart water systems, we see that it's not just the time scale, but also the scale in general. People in water systems, they sometimes use power systems in their own scale. Maybe they're using like they take an IEEE benchmark, like the 14 bus system, and they plug in like a local network, like an urban water network, which is not realistic, and vice versa. Power people, they plug in like they have their own system, but they plug in something like a national scale water system, which is not or a very simplified version of a water system, which is also, as Mathaios said, it's not accurate. So what we have been trying today is actually to raise the awareness and to understand that there are differences, and we shouldn't be taking lightly, let's say this, but use the appropriate network and the appropriate time frame. And of course, they don't have to be the same at the same time frame. I mean, it's okay to have delays. It's okay to work in minutes and power system in this is a high frequency system. It's in millisecond, let's say, but we really need to understand how power systems work and what they expect, how they expect the different devices to operate, and the assumptions that they are making. So, like, how much delay can we have in starting a pump? The challenges. So all of this, we need to put them in the discussion, in the discourse, in the next few lectures and discussions. So I think this is very, very important for us to gain a common understanding. It's not going to be a perfect analogy. I just want to clarify, because also this is a misconception that I also maybe sometimes use in my course. I use like the power and electric analogy, but there are differences. Especially they kind of seem similar, but they are not similar. But they have. So just embrace the similarities and understand the differences. And I think the fact that we have two people, like we have the water community and we have the power community dealing with this topic, I think it's a great initiative and a great opportunity for us to synergize into something and learn into something useful.
Okay. We have one more quick questions. This is related to because as you mentioned, Dr. Eliades, initially we have different challenges both in the power systems and water systems, and when we want to try to combine them. From all these challenges, in your opinion, which of the challenges is the most pressing to address now, and why?
I think Mathaios is more suitable to answer this. Like which challenges, especially in power systems, are more critical for that the waters that could affect, let's say, or how the water system could influence power systems. So I would pass this question to Mathaios.
Thank you, Dimitri. You're so nice. Thank you. So in energy systems, when we are talking about the energy transition, we look at this more from a holistic approach. And the water pumps and the water infrastructure is usually a big energy consumer. And the other way around, I mean, we depend on water for cooling, we depend on water for cooling, for hydropower, and so on and so forth. So at the simulation level, at the modeling level, at the academic level, I believe we are making some good progress with initiatives like this from FARAC to bring people together and discuss things. I believe the biggest challenge that we have is bringing the decision-making bodies together and coming up with a common, let's say, regulatory framework or common understanding of how to bring different systems together and how to make decisions that actually affect the interconnected systems and not just in silo. Now I'm part of the climate resilience expert panel of Ofgem, the regulator in UK, and we had a meeting yesterday, and this was raised as a high priority in the agenda of Ofgem in UK to basically sit together and talk with Ofwat. Ofwat is the water regulatory body in UK, and because during water droughts, for example, the licenses that the thermal generation site is buying for cooling, it increases a lot in terms of money. And then the electricity bills increase a lot. So this kind of cascading effects between the two systems is not properly captured in the policy and regulatory frameworks in order to drive investments in a more coordinated way. So I think from the modeling side and the tools methodologies perspective, we're making good progress. But the people sitting on the decision-making chairs, let's say, need to come closer.
So just also a quick comment from my side, maybe from a technical point of view. I mentioned on a different point of view from what Mathaios is saying. I agree, of course, with Mathaios. I think it's from a technical point of view, it's very important for us to start understanding how power and water systems are interconnected, especially in the context of microgrids. So I mentioned about these smart IoT devices. Power people they have a lot of people working with power electronics, with control systems, etc. And essentially they are the points where decisions are made at the local level. So it's like having a smart DMA, let's say, in water systems speak, right? Like having an agent making some decisions, and this is this is how the system will work in a few years. Maybe I don't know if it's going to be in your countries or it's going to be more in Africa or in other countries. It's something that we will see, but it's going to be there, and it's going to accept. If you read the IEEE standard for the microgrid controllers, it accepts an input. It accepts inputs from external systems, external agents. And essentially, our system, water systems are an external agent, as many others, of course, like big industries, etc. So we really need to put ourselves and adapt what we are doing into something that is there are already some standards, there are already some expectations from these systems. Water system is not something exceptional. It's a load in the system that can cause some it can cause some inductive loads. We know that we can shift the load depending on the situation. So we really need to start thinking of how these things in practice and understand what's happening in the reality of power systems. So like on the ground with the technologies, with all of these in smart controllers, etc. So I would say that this is a challenge for me. It's more technical to understand what's happening, which is of course is more feasible to achieve than what Mathaios said, which is of course to bring the policymakers and the decision makers together to agree on a common approach. But probably technology will be faster in this respect.
Thank you. Oh, Dr. Panteli, you want?
No, it's okay.
Thank you so much, Dr. Eliades and Dr. Panteli, for the presentations and the discussions. We truly appreciate it, and we have no more questions added. So before we sign off, I want to extend a huge thanks to Dr. Eliades and Dr. Panteli for the presentations, and to each of you that have attended the webinar. We hope that you get valuable information from this webinar, and please don't forget to also let us know the feedback of this webinar, and if you have any future topic that for us to cover, please do access the link that we have shared through chat. Thank you very much, everyone. We hope to see you.
Thank you for the invitation. I hope you enjoyed it.
Thank you very much as well. It was a great presentation.
Thanks,
Thank you.
everyone.
Thank you.
Have a great rest of the
Bye all.
day.
Bye bye.